When we hear the word elasticity, the first picture that comes to our mind is something like this. But is this really what elastic means? We will find that out in this video. Let's take an example of a helical spring. When a force of compression or tension is applied, the helical spring gets deformed, that is, it changes in shape or size. This force is referred to as the deforming force. And the ability of an object to regain its original shape when the influence of this deforming force is removed is called elasticity. More examples of such objects include sponge balls and rubber bands. When compressed or stretched, they get deformed, but they soon return to their original shapes. This self-reversing deformity the object goes through when forces applied and removed is called elastic deformation. But is there a limit to the elasticity of an object? Do elastic objects remain elastic forever? Not really. For instance, if a great amount of force is applied to a spring, it simply won't be able to stretch further than a certain point. But if the force becomes excessive, the spring will get permanently deformed and may even break if we keep increasing the force. Hence, the spring does not remain elastic forever. This type of deformation, where the object is unable to attain, or if it only partially attains its original shape once the deforming force is removed, is called plastic deformation. Now let me ask you a question. Suppose we have a rubber string and a string made of steel, both of very tiny thicknesses. Both are identical to each other in terms of size and shape. If we stretch them from both the ends with equal and opposite forces, then which one will stretch the farthest, assuming the deformation is elastic in both the cases? Quite obviously, the rubber string will stretch the farthest. The steel string would barely stretch, but it is important to note that it would indeed stretch no matter how little. It doesn't stretch as far as the rubber string because steel applies more resistance to the deforming force than the rubber does. Moreover, as soon as the force is removed, the steel string regains its original shape and size quicker than the rubber string. It won't allow a deforming force to change its dimension as easily. So, which one would you say is more elastic? Steel or rubber? You would think that the obvious choice has to be rubber, but unfortunately, that's incorrect. There is a general misconception that a lot of us have about elasticity. We think that the more the object gets stretched or compressed, the more elastic it is. But elasticity is not the same as flexibility. In the language of physics, the term elastic has a very different meaning. In physics, we say a body is more elastic if it resists more to the deforming force and reverses back quicker to its original shape after the force is removed. And since steel resists more and reverses back to its original shape quicker, it's more elastic than rubber. We can mathematically define elasticity as the ratio of stress to strain. We'll teach you what stress and strain mean in the upcoming videos. But get ready to be hooked to our next video on Hooke's Law. What are elastic and plastic deformations? Well, deformation means the change in shape and or size of the body. And the force which deforms an object is called deforming force. Elastic deformation is the case of deformation where the body regains its original shape as soon as the deforming force is removed. But what really happens? In a state of deformation, there is a restoring force generated inside the body resisting the deformation. Yes, a restoring force. When the body is in equilibrium, this restoring force is equal in magnitude to the deforming force and acts in opposite direction. And as soon as we remove the deforming force, this restoring force comes into play and restores the body to its original shape. Plastic deformations, on the other hand, are the deformations that permanently change the shape of the body. The applied force here is simply too much for the body to bear, and that results in permanent deformation. Now, which objects show elastic deformation and which ones show plastic deformations? Generally, all the objects show both types of deformations. Yes, for instance, if we just keep extending the spring forever, there will be a certain limit beyond which the length won't increase further. And if we try to apply more force, the spring may loosen and end up breaking. So the spring shows elastic deformation up to some extent, beyond which it results in plastic deformation. Spring is like a common example. Generally, almost every object shows both elastic as well as plastic nature. The elastic limits depends on the deforming force applied on the object and the properties of the material they are made up of. And it is important for engineers to note the elastic limits of things such as metal beams and concrete. That is, the limit to which they can uphold the load without getting permanently deformed or cracked. Now we come to an extremely important topic. The Hooke's Law. Robert Hooke, an English physicist, stated that the empirical law in 1660, which is today known by the name Hooke's Law. What does empirical mean? It means the law was derived using observations. It states, for elastic deformation in a string, the deforming force is directly proportional to change in length. Consider a spring of length L, whose one end is fixed from the end. Suppose the stretching force F is applied on the other end. Now let the change in its length be delta L. The law states that the force F is directly proportional to delta L. Now, what do we mean in mathematics when one quantity is directly proportional to the other? It means that one thing is some constant times the other. So we can write force F is K times delta L, where K is the proportionality constant. This is the mathematical form of Hooke's law. In some textbooks, you must have noticed the presence of negative sign on the right side of this equation. The negative sign comes due to the slightly different version of the Hooke's law being followed. We can also define Hooke's law as the restoring force is directly proportional to change in length, and this of course is valid for elastic deformation only. The force taken here is the restoring force and not deforming force. The negative sign only tells us that the restoring force is opposite to the direction in which the length is changing. Another thing is that this law is not only valid for elastic deformation in a spring, it's also valid for elastic deformation in any material. But there is an assumption that this law is valid when the forces and deformations are relatively small. Also, there is a modified version of Hooke's law. It says that in an elastic deformation, the stress experienced by a body is directly proportional to strain. Before understanding this modified version, we need to understand what stress and strain mean. And we will do that in the next video.